The bell work today is calculating molar mass, and we are trying to find the molar mass of methane. Methane's formula is CH4, so what I'm going to do is write out the elements C and H. I need to find the molar mass from the periodic table for these elements. Carbon's molar mass is 12.0, and hydrogen's is 1.0. And then from there I need to find out how many atoms there are of each element. And for carbon there is just one, so I'm going to multiply that by 1. For hydrogen there are 4 atoms. When I multiply these out, I'm going to get 12.0 for carbon, and I'm going to get 4.0 for hydrogen. To find the molar mass, I simply add them up, and I'm going to get a value of 16.0. And so this 16.0 has units of grams per mole. So yesterday in class, we talked about our first conversion factor using the mole concept, and that was with representative particles, with molecules, atoms, ions, or formula units. Our examples consisted of atoms and molecules. We didn't really talk about formula units and ions, but just know that those can be part of representative particles. Today, we're going to move on to our second conversion factor, which has to do with molar mass. So yesterday, or today in class, you learned how to calculate, how to add up the masses from the periodic table to find a gram formula mass, or gram molecular mass, or molar mass, or molecular weight. There's lots of different names for that. So that's what we're going to learn today, but we're going to use that value as a conversion factor, and it's going to be our second one. And then towards the end of class, there's going to be a third conversion factor that involves a volume of gas. So this new conversion factor is going to take the mole concept, and instead of converting it into representative particles like molecules and atoms, we're going to convert it into mass, or grams. And to do that, we're going to use this new conversion factor. So I'm going to give this guy a puffy cloud of greatness, which means that this is very important. Okay, and the mole conversion chart or diagram that I gave to you is going to come in handy. So we worked on the bottom right portion of the mole diagram. Today we're going to focus on the bottom left. And the conversion is this. We can have, for every 1 mole of substance, whatever it might be, over the gram formula mass, and again, that is a calculated value by us. We have to calculate that. Or it can be the gram formula mass on top over 1 mole. Now, we got to be careful, because depending on what we're trying to do, we have to make sure that our units are canceling top and bottom. So our first example is to find the mass in grams of 3.32 moles of potassium. That's the symbol K. And this diagram is going to come in handy, so we want to learn how to use it so that it'll help us. Yesterday we focused on this bottom side of the quadrant here with representative particles. That could be, atoms, or molecules, or ions, or formula units. Today we're going to focus on this side of the quadrant here with molar mass. So this is going to involve grams, and we're going to be using the periodic table. So the first thing I need to do is go ahead and draw my line for my T-chart so that we can get started on this. I'm going to start out with 3.32 moles of potassium. Okay, because that's what the problem gives me. Now, what comes next? I am using gram formula mass as a conversion factor. And again, to do that, and any time that I add up those periodic table values, it's going to be some sort of number that we calculate, and it's going to be grams per mole. Okay, so how am I going to put this in to the T-chart here? Well, it's going to go something like this. we are going to take the mass of potassium, which is 39.1, and we took that straight off the periodic table. So it's going to be 39.1 grams per every 1 mole. So in every single mole, there's going to be 39.1 grams of potassium. Okay, and what happens is moles are going to cancel out, and we're going to be left with grams. And that's what we wanted. We wanted to find the mass in grams of potassium. The answer I get is going to be 129.812. Now, what does sig fig say? Sig fig says that we were given a measurement of 3.32 moles, which had 3 sig figs. So I just need 1, 2, 3. The 8 is going to round that 9. And so overall, my final answer should be 130, and I have to include a decimal point, because if I don't, then I will only have 2 sig figs, and that's going to be grams of potassium. That's how I finish it. So that is my final answer right there. Our second example says find the mass in grams of 15 moles of sulfuric acid. So let's look at our diagram. If I am going from moles and I'm trying to find the mass, okay, I'm going to be traveling this way on the diagram. So all you have to do is follow the road and you'll get to the conversion factor that you need. Well, either way, I am using mass and I'm looking at moles, so I'm going to have to use gram formula mass. So I'm going to have to go and find that for my compound sulfuric acid, which is H2SO4. So the first thing I need to do is write out the elements that I have. So I have H, S, O, and those are the 3 elements that I have. So I need to go ahead and find the weight on the periodic table of these. Hydrogen is 1.0. Sulfur is 32.1. And oxygen is 16.0. After a while, you'll probably start to kind of have some of these values memorized, ones that are common like carbon, hydrogen, and oxygen. Some not so much, but you'll always have a periodic table to use, so don't worry about that. Next, I have to find how many of each atom there are, and so with hydrogen, I have 2. So I'm going to multiply this one by 2. Sulfur, I have just 1, and oxygen, I have 4. So hydrogen is going to give me a total weight of 2. Sulfur is going to give me a total weight of 32.1. And then 16 times 4 is 64. So to find the molar mass, all I have to do is add all these values up. And let's see, I get a value of 98.1 grams per mole of sulfuric acid. So now I can go ahead and come in and fill out my T-chart, starting with 15.0 moles of H2SO4. To convert from moles into grams, I'm going to use molar mass. I have 98.1 grams per 1 mole of H2SO4. And moles of H2SO4 cancel top and bottom. So I am left with grams, and that's what I wanted. I wanted to find a mass. I wanted to find a mass of sulfuric acid. So after calculating, the answer that I get is, with correct sig figs, will be 1470, and that is going to be grams of H2SO4. And that is my final answer here. The next one says find the number of moles in 11.0 grams of methane, which is CH4. In the Bell work, we completed the molar mass of methane, so right away we know that the GFM, the gram formula mass, or what we call molar mass, is 16.0 grams per mole, which is nice, so we don't have to do that calculation. So we can go right into our T-chart. Find the number of moles in 11 grams of methane. Well, this time we are given grams. So we're going backwards on the chart. If we're starting with grams and we're trying to find moles, we're going to be traveling this way on the diagram. So you just got to follow the right road and it'll give you the right conversion factor. So let's start with 11.0 grams of CH4. And again, I'm starting with grams, so that's why I wrote it in red, okay, so that we understand that we're starting with something different this time. Now, I need to use my molar mass conversion factor, my GFM, in order to go from grams to moles. So in this case, 16 is going to go on bottom, 16.0 grams of CH4 for every 1 mole of CH4. And so my units cancel, grams of CH4, and I'm left with moles of CH4, which is what I wanted. So I'm good. I can draw my finish line here. After I calculate, I get an answer of 0.688, and that is with sig figs, and my units, moles of CH4. And that is my final answer. Next, we're going to move on to a little bit more complicated problem. This is going to be a multi-step mole problem, or a multi-step problem. It says calculate the number of molecules, which is a representative particle, present in 4.29 grams of nitrogen dioxide. So we have representative particles and we have grams, which is a mass, so this is going to be a two-step conversion. So on my chart, I'm going to be converting to moles, that's step 1, and then from moles I will be converting to representative particles. So step 1 here is going to be going from grams to moles, and then after that, moles to molecules. So I'm going to go ahead and write in blue for the first step. To go from grams to moles, I'm going to go ahead and I'm going to need a gram formula mass, or a molar mass, of NO2. So that's exactly what I'm going to do. I'm going to have nitrogen and oxygen. The mass for nitrogen on the periodic table is 14.0. The one for oxygen is 16.0. I have 1 nitrogen and I have two oxygens. So for nitrogen, I'm going to have 14. For oxygen, I'm going to have 32.0. When I add these up, I will get 46.0 for my molar mass. So I'm going to do this in one T-chart. I'm going to start out with 4.29 grams of NO2. I'm going to use my molar mass, 46.0 grams of NO2 for every 1 mole of NO2. Next thing I need to do is go from moles of NO2 into molecules of NO2, and this is what we did yesterday during notes. So I'm going to use a different color here. This will be step 2. I'm going from moles to molecules. So in every 1 mole of NO2, I know that there are 6.02 times 10 to the 23rd molecules of NO2. And so what happens here is grams of NO2 cancel, moles of NO2 cancel, and I'm left with molecules of NO2, which is what I wanted. So after calculating, I get an answer of, with correct sig figs, would be 5.6 0.61 times 10 to the 22nd molecules of NO2. And that would be my final answer. In this problem, it's the same thing. We're going to be doing a multi-step problem, but we're going to be throwing in a little twist here. It says calculate the number of moles of sulfur atoms present in 2.01 grams of sodium sulfide. Well, the difference here is that we're calculating the number of moles of sulfur atoms, but we're talking about a specific compound, Na2S. So we're going to look at specifically the sulfur atoms, not necessarily the molecule, the compound. We're going to look at just the atoms of sulfur. So first I need to look at my chart and figure out where I'm going. I'm going from, it says calculate the number of moles from moles of sulfur atoms. So I'm going to atoms from grams. So I need to go to the moles first and then from moles to representative particles. So I'm going to calculate molar mass first. So I'm going to start out with 2.01 grams of sodium Na2S. That would be sodium sulfide. To go from grams to moles, I need molar mass. So I'm going to do that up here. I have sodium and sulfur. Sodium has a molar mass of 23.0. Sulfur has a mass of 32.1. And there are two sodiums, and there's just one sulfur. So I'm going to have 46 grams worth of sodium and then 32.1 grams of sulfur. So when I add these up, I'm going to get 78.1. So I'm going to take that and put it in 78.1 grams of sodium sulfide for every 1 mole of sodium sulfide. So now I've successfully gotten into moles of sodium sulfide. Now I need to go from moles of sodium sulfide into sulfur atoms. So how do I do that exactly? All I need to do is know the conversion of how many atoms are in this molecule. Well, in this molecule, sodium sulfide, I have 2 sodiums, but I only have 1 sulfur. So I'm going to say that in every mole of sodium sulfide, Na2S, I have precisely 1 mole of sulfur atoms. If I had a different subscript on sulfur, this number up top would be different. But I only have 1 atom of sulfur in there, so I can say that I have 1 mole of it in each compound. So I am completely finished now. After calculating, I get an answer of 0.2. Excuse me, that's incorrect. I have an answer of 0.0257 moles of sulfur atoms. So that is my final answer. Next, I'm going to calculate the mass in grams of 2.49 times 10 to the 20th carbon dioxide molecules. So I'm going from molecules to moles and then moles to grams. So another multi-step problem. Here's my line. I'm going to start out with 2.49. 2.49, I'm going to use the term E here, which means times 10 to the 20th, and this is going to be CO2, and I'm just going to put M for molecules so I can save space here. As long as I know exactly what that means, that's okay. So I'm going to go from molecules into moles. Well, how do I do that? I know that if I have 6.02 and I'm going to use E again to save space. 6.02 E23 molecules of CO2. Then I have exactly 1 mole of CO2. To go from moles to grams, I need molar mass. So I got to find the molar mass of carbon dioxide. Well, carbon and oxygen are the two atoms I have. Carbon is 12. Oxygen is 16. And I have 1 carbon. And I have 2 oxygens. So I have 12 plus 32. That's going to give me a value of 44 grams per mole. So 44 grams of CO2 for every 1 mole of CO2. And I do that so that moles on bottoms can cancel. And I am done. So I just got to calculate now. And the answer that I get is 0.0182 with sig figs. And that will be grams of CO2. This one has a little monkey wrench in it as well. It says calculate the grams of carbon in 12.2 moles of sucrose, which is a sugar. And the formula for sucrose is C12H22O11. Sounds a lot like glucose, which is C6H12O6. These complex sugars have the same basic structure and formula. They might just have a different number of atoms within them. So we are trying to calculate grams of carbon from moles of sucrose. So this would seem like a one-step problem, but there's something that's interesting. We're looking for grams of carbon in a compound that has elements other than carbon. So first things first, I'm going to go ahead and draw my line out and write what I'm given, which is 12.2 moles of sucrose. And I'm going to put an S here to save space. That's going to represent sucrose. So first I need to go from moles into grams. But first I want to narrow down my compound that contains more elements than just carbon into carbon. So looking at sucrose, I see that there are 12 carbons in here, and I want to isolate those. So here's how I do it. I am going to say that in every 1 mole of, and I'll go ahead and write out sucrose here, C12H22O11, in every 1 mole of, and for every 1 mole of this sucrose molecule, there are 12 carbon atoms, which means I will also have 12 moles of carbon. So I've gone from moles of sucrose into moles of carbon, just using the ratio of the elements in that compound. So now I can go from moles into grams using molar mass. And so for every 1 mole of carbon, this is going to be its molar mass, and I'm taking this straight from the periodic table. It's going to be 12.0 grams, which is 12 grams per mole. That's the molar mass. And so I'm done. And after I calculate, I do get an answer of, and let me write this out, 1.76 times 10 to the third grams of carbon. So, moving on, we're going to go ahead and look at, briefly today, the third conversion factor, which is moles, and we are looking at volume. So far we've had representative particles, we've had gram formula mass. Now we're actually going to be looking at how the mole relates to volume, specifically volume of a gas. So at STP, 1 mole of any gas has a volume of 22.4 liters. Well, STP we're going to cover in the next slide, but 22.4 liters is how much space any gas will take at a certain temperature and pressure. We call it molar volume, and it's going to contain the same as 6.02 times 10 to the 23rd particles of the gas. So all of these things that we're learning are related. So that mole diagram that you have shows the relationship. 1 mole equals the molar volume of a gas, the representative particles, Avogadro's number, and also this gram formula mass that we've learned. So we have 3 conversions. This was the first one that we learned, and then the gram formula mass was 2, and then we're finally stepping into this third conversion factor. So the volume of a gas happens at what we call STP. So what is STP? It stands for standard temperature and pressure. Well, what is the standard temperature and pressure? Well, the standard temperature and pressure, the temperature is 0 degrees Celsius and 1 atmosphere. So these standard temperature and pressures are basically at room temperature and room pressure, what we're sitting at currently in this room. So to have this value of 22.4, which is how many liters of gas, how many liters of space a gas takes up, it has to be at these conditions, or else the value would change. It would no longer be 22.4, it would be something else. So our third and last conversion factor for this unit is right here. So I want you to go ahead and give yourself a puffy cloud of greatness. We have, this is going to be number 3 of 3. We only use this for gases though, so there's kind of an exception here. Volume we can only look at with gases. So in this conversion factor, this will always be for compounds that are in the gas phase. So here's an example. What is the volume in liters at STP, that's standard temperature and pressure, of 0.960 moles of methane? And that's a gas, methane gas. So we are starting with moles here in the center, and we are wanting to know what the volume is. So we're going up top to this third quadrant. The process of dimensional analysis is the exact same. We're going to start with 0.960 moles of methane, CH4, and we are going to move from moles into liters of gas. So the conversion factor here, for every 1 mole of CH4, that gas is going to occupy 22.4 liters of space. And that is going to finish us out. So moles cancels, and we're left with liters. Liters of what? I didn't fill it in. This should be CH4. And the answer that I get is going to end up being 21.5, that's with sig figs, liters of CH4. And our last example for today, it says at STP, standard temperature and pressure, 0 degrees Celsius and 1 atmosphere, how many moles are in 0.542 milliliters of neon gas? I'm going to start out by drawing my line. I'm going to start with 0.542 milliliters of neon gas. So I'm going to put Ne, that's the symbol for neon. The conversion factor that I've learned is 22.4 liters of gas for every 1 mole. And I'm given milliliters. So I need to convert milliliters into liters so that I can use my conversion factor. There are 1,000 milliliters in milliliters of neon, let's be specific, for every 1 liter of neon. So that conversion factor will always be the same. 1,000 milliliters in 1 liter. I threw neon on there just to be specific. So now I'm in liters of neon, and I'm trying to go to moles. So liters to moles, I'm going to follow that path. 22.4 is going to go on the bottom so my units can cancel. 22.4 liters of neon for every 1 mole of neon. And I'm done. Milliliters cancels, liters cancels, and now I'm left with moles, which is what I wanted. And the answer that I get is going to be 2.42 times 10 to the negative 5th moles of neon.